Second, yeah, I think the recording has started as well. I think we are good to go. Most of the people have joined in. So just to kick it off, so we have Ankit with us, qedk, famously known as over Twitter and our Discord as well. He is the technical mentor and also currently works with Polygon. And most of you already know that was a track one fellow from EIF 2.0, and the journey for him has been pretty awesome, even like for us to witness such amazing growth over the year. And yeah, like since yesterday we released our coursework, we this week is mostly going to be on smart contract dev. Like last week, we pretty much did a very basic deployment where you literally had to copy paste code while understanding them. And but now this week it's a more deeper dive into writing smart contracts where you're actually going to be doing it yourselves. And to facilitate that, Ankit will be sort of walking you through over like the basics, the important things, and what things need to be taken care of. Uh, yeah, Ankit, over to you.
All right. Hi everyone. Just to introduce myself, I'm qedk. I'm a smart contract engineer at Polygon, and I'm here to kind of just do a intro to smart contracts. Um, okay, I see a question. What's qedk? Really nothing. It means nothing. Okay, it is if you have heard of the webcomic XKCD, so
Yeah,
essentially Randall Munro, the way it was named was like you can't say the four letters together. And I was like, sounds good, I'll do that. While doing that, I realized that people were saying my name in the weirdest of ways. So some people are saying qedk, some people are saying quedk. After a while, I just gave up. So say it any way you want it. It's fine, really. But yeah, it means nothing. All right, I think we should just get started. But just to kind of, I guess, don't blame me if it's shit. I was trying to do this on time, and it turns out that I can't do things on time. So we'll let that pass. And let's go. Let me find the screen. All right, you guys can see it, right?
good to go.
All right. All right, let's go. All right, so this will just be a basic session on smart contracts. So it's smart contracts 101. Let's move on to the next part, right? So the first question that I feel we kind of need to tackle is like, what exactly is an EVM chain? So obviously we all know it's a blockchain, right? We know that there are blocks, the blocks are linked to each other cryptographically and all of that stuff. Um, but this is where I guess the core aspect of Ethereum comes in. So essentially, in Ethereum is like a distributed state machine. So then the question can be, well, what exactly is a state machine? And you can kind of think of it as like as an abstract computing concept where essentially there's a machine. We have defined it something as a machine, and then it goes through these particular distinct states. And that is technically what Ethereum is. So you have state one, and it moves on to state two, state three, state n through distinct steps. And the reason it's essentially called a distributed state machine is that you kind of can simulate it from one node to another, and it performs exactly the same. The reason it performs exactly the same is kind of more harder to answer, but technically you can kind of think of it as a set of computers who have chosen to follow the rules that have been imposed by the EVM, and essentially which is they are agreeing that, yeah, I agree to these rules. This is the result of the computation, and that is how you get this huge distributed state machine. So essentially, you have like accounts, balances, which you can kind of think of it as a database, right? But you essentially also, apart from that, you have the concept of storage that we'll kind of address to later. And the idea is that these rules can kind of also change. And when these rules change, those kind of happen as like hard forks or soft forks, which again will not be tackled today, but are probably good to keep in mind. So let's move on to the next question that we can have, which is, what exactly is a transaction? Um, in other chains, right? It's very easy to understand what a transaction is. There are these concepts called UTXOs, which is unspent transaction outputs, which I guess other blockchains use. But in Ethereum, it's slightly more complex and more interesting. So essentially, let's talk about a chain where you just transfer some balance, right? The transaction only needs to do that particular one thing, where it's like remove from A, add to B, whatever, right? It's obviously not as simple as that, but just as an example. For Ethereum, however, a transaction is a state transaction function. So we already know that Ethereum is technically a state machine. So what that means is each transaction is changing the state, the world state by whatever, if it's changing at all. Technically, it always is, but that's a nuance for another day. And so essentially, you can kind of think of it as like a function like YST, and then you essentially get S naught. So essentially, where it's the world state before TX execution, and then you have a new world state after the TX execution. Now, when we talk about an Ethereum transaction, those can technically only be sent by externally owned accounts, or as we call them, EOAs. Um, the reasoning behind why is a bit more nuanced. We'll kind of come to that more as we kind of talk about smart contracts. But for now, you can kind of think of it as any action that has been initiated by an EOA on the blockchain. So let's go to the next one, which is like, what is an address? Um, Ethereum addresses are technically just a derived form of an ECD as a public key. So essentially, you can kind of think of all your MetaMask wallets or like cold wallets like Ledger, whatever. They essentially always have a public key and a private key. And since Ethereum makes use of the ECD as a signature scheme, particularly with 256-bit keys, you essentially have a public key that is derived from the private key, which is also 256-bit. And to get the Ethereum address, we essentially just hash it. So we do a qedk 256 hash of that particular public key, and then we just get the last 20 bytes, and that is what the Ethereum address is. The reason to have it 20 bytes is primarily because at the point when it was set, it was decided that it is large enough to avoid collisions, but small enough to be readable and looks good. Now, it doesn't look good, obviously, but for what it's worth, that is how the Ethereum address came to be, so to say. And then finally, we come to the question of what exactly is a smart contract. So technically, a smart contract is a program that runs on Ethereum blockchain, right? Obviously, more nuanced than that. But if you want to think of how a smart contract functions, it is similar to that. The code is on the blockchain. You provide it some call data, and then it does whatever it's supposed to do. But I guess what makes it really special is that since we kind of have already kind of established that you have the concept of this EOAs and you have the concept of a smart contract, is that an Ethereum account can also have data attached to it, so to say. So which means that if there is any data that is stored at that particular address, we can kind of fetch it and do whatever we want with it. And finally, we come to the fundamental distinction between a smart contract and an EOA, which is that a smart contract cannot send transactions. The funny thing is that this was kind of a kind of an assumption in the EVM, right? That smart contracts cannot send transactions, but until like around 2 years back, I'm not sure, is kind of when it was finally enforced and made into an EIP. So up until that point, theoretically, if you did find the private key to a smart contract address, you could potentially access those funds. But with the new EIP and kind of every miner sort of already consenting to it, it is not a possible attack vector anymore. And obviously, we have to understand that since the address space is so big, it is simply not feasible for you to just go ahead and brute force and try to find such a private address that corresponds to that particular address. And the reason why EVM it is what it is that it kind of treats all accounts as the same. So from an EVM perspective, smart contracts are essentially the same as EOAs. So if a smart contract were to call another smart contract, or if you were to use a transaction and make a message call to a particular smart contract, for the EVM, it looks exactly the same. It doesn't really care. Obviously, there are ways to kind of get around it. Um, so like we will kind of come to those later, but the basic concept is that the EVM was meant to be like this highly composable ecosystem where contracts and end users can both kind of build off each other. It doesn't need to be like distinct, right? Which other blockchains don't do it that way. So ideally, you have the concept of reserved namespaces. So essentially, what it means is that it doesn't matter what private key you find. It doesn't matter what private key you have, but from one set of address to another, like let's say 0x001 to 0x0ff, right? All of those addresses are just reserved. And typically what would happen is you would have contracts in those particular addresses, which are only available. And then everything else is just running using those. In EVM2, you have those things. Those are called pre-compiles, where essentially it's not technically a contract, but it is Go code that has been modified in such a way that if you were to make a message call, it would actually be executing directly off that particular Go code. Obviously not just Go, but any language that kind of chooses to implement the EVM, it would be using those instead. And let's talk about storage, right? So when when you come to solidity, you kind of have three options. You have the storage, you have memory, and you've call data. Again, like this is a lot of theory, I understand. I'm not a big fan of theory either. So I guess at the end of this, what we'll do is we'll kind of walk you through some random contract. I haven't really made up my mind. Um, and we'll kind of see how writing such a contract goes. But essentially, what I've tried to do is kind of break down the most practical components of a smart contract and the parts that I feel is the most like, what the hell does that even mean? And kind of get those jot down first. So the way it works is, even if you don't understand it, at a later point in time when you're either reading other code or you see me writing the code or you're writing your own code, you can just call back on this and be like, this is how it connects. So which is why I kind of want to delve into the theory first. But let's talk about storage. So essentially what it means is that any data that is defined as storage, it is part of the world state. Um, uh, so if you remember before, if we go back to this EVM blockchain, right, you have the virtual machine, you have some EVM code at an address, you have the machine state, you have the account storage, and then finally you have this world state. The world state is essentially like a persistent sort of data that is always there and is you can always access it. But again, it's important to remember that you can only modify your own data, right? Because otherwise, I mean, you gotta have rules. But yeah, let's go back to storage. So essentially, storage is any data that is stored at your particular address in some particular way. Um, and since this is the world state, obviously, accessing data from this is slow and resource intensive. There's a think why. Please do think why. We'll address this later. And then obviously, in line with those assumptions, it obviously costs the most to read data and store data in storage, which is the world state. Then you have memory. So essentially, data that is stored in memory is ephemeral. So essentially, it means that it doesn't really exist out of transaction execution. So after a transaction completes execution, it's as if that memory never existed. So it's basically like a byte addressable memory space that can be read and written to as much as you want. However, like if you're accessing or if you're writing something new, a memory only extends in full words. So let's say you even make use of like 1 byte, it's going to be extended up till for the entire word and not just that particular byte. There's a reason for that as well. We'll address it later. And finally, you have call data. where essentially what it means is that it's kind of the same as memory. However, the call data is typically it's the transaction call data, right? So it is essentially the data that we already know is provided to the transaction, which means that obviously it is immutable, right? Because you cannot go ahead post facto and change transaction call data. And finally, this only means that only external function parameters can be stored as call data. By external function, obviously, it means external and public. We'll come to those later. But essentially, the functions that are invoked through a transaction, only those functions can have data stored as call data, because otherwise it just doesn't make sense, like, right? Because otherwise you won't get any data as call data. And which is why it is immutable, and it is also the cheapest. Um, and theoretically it is infinite, but again, like talking about all of these types of data, it is theoretically infinite. So if you could ideally store as much data as you want, right? But you cannot, and that is primarily enforced through gas mechanisms. So by making this the most expensive, it disincentivizes your need to store the data in storage, because otherwise you would always want it to be in a world state. Why bother with anything else? And similarly, if you did it with memory, like, then ideally you could kind of expand the memory as much as you want and kind of DOS other people's transactions, which is why even the memory that storage here, usage here, the gas usage scales quadratically. So after a certain point of time, it just gets too expensive to use memory. Similarly, for call data, technically also theoretically infinite, but there is something called a block limit. So I don't think you can have. I think the maximum is around 1.8 MB, if I recall. So in that is the total transaction call data, by the way, for a block. So it cannot really exceed that. So you're always capped at a certain point of time for all of these kinds of storages, which obviously makes sense, because otherwise you could kind of DOS each and everything, which just doesn't work for a global blockchain. And yeah, finally, let's talk about a bit about inheritance. So Solidity does have multiple inheritance, including polymorphism. So what that kind of means is that you can inherit from multiple contracts at the same time. Um, but Solidity doesn't have it in the same way that you might think of in other languages, right? So like, let's talk about Python or Java for whatever sense. So typically, if you defined like a contract A, a contract B that inherits from A, and then have a contract C that inherits from both B and A, in Solidity that wouldn't compile. And the reason is because it treats them as independent contracts. So it's as if it would execute the constructors of both, and then it would treat them as if they're independent. But in other languages, they do a compile time optimization, where essentially if it determines that some previous contract has already inherited some other contract, it just doesn't care, and it just puts it right in. This is done using DAGs, but again, probably out of topic for today. But yeah, some fun features that I like using in Solidity is function overriding and overloading. It's technically very useful, but it doesn't really come into use as much as you think it is going to. Most people, when they use inheritance, they are just like, they're probably just inheriting from Open Zeppelin, and that's it, right? They don't really think about what's happening underneath that, which is, I guess, what I kind of wanted to address. But essentially, what is happening under the hood is that you're getting all of those contracts similar to how an inheritance works. So, which is why, you just write is ERC20. You inherit ERC20 from Open Zeppelin. Wow, it just works, right? But obviously, it's a bit more fun on the inside, because if you go through Open Zeppelin contracts as well, you can kind of get a lot of more nuanced understanding of how these token contracts work. So essentially, how it typically works is you have an interface contract, you have the main contract that is borrowing from several of these interfaces, and you can kind of add and remove components as well. Um, and that is kind of done through what is called function overriding, which is like if you're a person from OOPS, then yeah, you'd know it's called runtime polymorphism, where essentially it's determined at runtime which particular function to call. In Solidity, it's a bit more nuanced because if you want to override a function that has already been defined in a parent contract, you have to use the override keyword, which is kind of what makes it funky sort of way. So if you didn't put override, um, it would not do that essentially. But yeah, like it doesn't really have to match kind of any functionality. So you could kind of have entirely different logic in it the way you want it, and you can also change the view. Okay, actually we haven't come to that yet. We'll come to that later on. And then this is what's like a typical form of function overloading, right, where you have the same function name but a different function signature. So essentially you can have event x, you can have event x and event y, and theoretically you can do like any sort of combination you want as long as the function name is same but the parameter list is different. And then finally, we come to visibility modifiers. So this is actually an important aspect of writing Solidity, that obviously not every function needs to be callable by everyone. Um, and I guess another good reason of doing this is because it is cheaper to do it the right way than do it the wrong way. So let's say that you have a public function, right? And it just works, right? People can invoke it as any way they want, and the contract internal functions can do that as well. However, what that means is that the compiler is not able to make the optimizations that it can. So um, when you talk about functions, essentially what you can kind of think of it as in Solidity is that you have the function name from which you get the function selector. So at any point of time that you make a transaction, if you go and look at the transaction, you will find that you're kind of providing that particular function selector in the transaction call data. Now, the question obviously arises, like, why do we need that? And the reasoning being that that is what the Solidity code uses to find the particular function that you want to call. So by optimizing on this particular front, the compiler will not generate those selectors internally. So it's as if that you can kind of use it the way you want it to, but the internal contract functions will not be able to see that, which kind of makes it somewhat cheaper, but it's also a good practice to do it, obviously, right? Um, all right, so let's go through all of those visibility modifiers. Yeah, so first we have the external modifier, right? So essentially functions that are defined with this modifier can only be invoked externally, um, which means that it can be a message call from another contract, or it can be like a transaction call by an EOA. And these functions are visible in child contracts as well. For public, it's kind of the same, but the functions are also, the function selectors are also visible internally in the contract. So it is essentially accessible to the internal and private and external functions as well. For internal, these functions are only invoked internally, so they cannot be invoked by other contracts or by an EOA. And these functions can be kind of inherited the way you want it to be. And finally, you have private. It behaves the same way as any internal function, with the only distinction being that these functions are not visible in child contracts. Um, and that is pretty much the four visibility modifiers that we have. Um, for variables too, you have visibility modifiers, except you don't have external, right? Yeah, so you only have public, internal, and private. Typically, all state variables are by default internal. What that means is that you cannot access it or see it out of the contract. And so literally the only thing happens when you define it as public is that Solidity creates an automatic getter function for that particular variable. So if you had a state variable g, which is public, you could just do contract.g, um, invoke it like a function, and then you'd be able to see that particular variable, which is not the case for internal, which is obviously why internal and private variables are also cheaper. Um, in most cases, you don't need more than private. If you want if you want it to be accessible publicly, then you obviously need public. But an important thing to understand is that private doesn't mean private. So this private, the word really, all it signifies is that it is invoked internally and it's not visible outside outside the contract that is currently defined in. It doesn't mean that someone cannot see it. So they can just decompile the bytecode to kind of find that particular variable at all times. Um, this is kind of a misconception that exists early on when you were in the space. But essentially there is no private form of information. Any data that is on the blockchain can always be read and always be accessed. Obviously, there are mechanisms for keeping data private, typically encryption algorithms, but probably also a question for a later day. And finally, we come to understanding exceptions, right? So typically, you have really three choices of error handling in Solidity. And the most important thing to understand is that all errors in Solidity are state reverting, which means that if there is an exception, which is essentially either the revert OP code or the invalid OP code, it's going to revert the entire call stack before, or that has been done up to that certain point. So it is as if those changes never happened. So yeah, so first we have the revert. This is kind of the most simple form of a exception. So you kind of just use the revert keyword, and then you either use a custom error or you provide it a string. And since it uses the revert OP code, it kind of refunds all the remaining gas as well. Then secondly, you have require, which takes in two arguments. The first argument, if it is true, then it just continues with the execution. And if it is not true, then it kind of, if it uses the string as an error string, refunds the remaining gas, and then reverts all the state changes. Assert kind of behaves similarly, except it uses a different OP code, which is the invalid OP code, which consumes the rest of the gas that isn't provided in the TX. And that is pretty much the only distinction. But let's talk about why these errors are the way they are, right? So typically, in most cases, you will mostly be using require. The reasoning for that is require is used to protect against invalid input. So it means that if the input, if a user input doesn't behave the way you want it to, then you should be using require. And which also means that if a user gets it wrong, they're kind of getting that remaining gas back, which is what we want, because they made a mistake, so it doesn't really make sense to waste any gas on execution. Um, Revert kind of behaves the same way, right? Except um, since the new Solidity versions, you now have the option of defining custom errors instead of string errors, which you kind of save a bit of gas by doing that, because you're no longer using a string and kind of using that entire word of memory. So that is, I guess, one advantage of using revert over require, but they're typically used for the same scenario, that they're used to invalidate or validate user input, and depending on that, kind of either let the transaction continue or revert. And then the reasoning for assert, and the reason it consumes the rest of the gas, is that it's used to protect against what's called invariants. What that means is that these are essentially things in the contract that are defined to be invariant. So they should like never change. And the fact that that condition will be false means that something has gone wrong, like definitely gone wrong. And that is the kind of the only use case for assert that is kind of not covered by require. So which means that require is typically done at the start of function execution to check if the input is what you expect it to be. And assert is kind of done at the end to kind of assert that, yes, the contract state is what it should be. Um, and it's really a fundamental part of kind of control flow in Solidity. And by using require and assert, you can kind of use other algorithmic structures, like you have things like SMT checker, which can kind of automatically fuzz things. So stuff like forge, right? Forge fuzzing, or like if you run your something like a qedk, all of them can use these parameters, like provided in reward required, actually just require and assert, and check against those conditions. And they can try to find points where it kind of fails or where it reverts. So which is why it's a good idea to kind of understand the use cases of these two statements and kind of where to kind of use it exactly. With that, we kind of come to the end of the theory part of it, so to say. I'm not sure if you all expected more or less, but I guess that's pretty much all I had for 101. But before we move on to this, um, I didn't really plan exactly. Oh wait, yeah, my bad. Yeah, so I didn't exactly plan what to write as a contract, so to say. I was just thinking we'll kind of either write an NFT or an ERC contract, not from the standard, but from like the use case we want from scratch, and then maybe you can kind of walk through that. But what do you guys think? What do you think we should do? Aniket, if it's not the fellows, it's gonna have to be you, I think.
Yeah, I'm pretty sure it's gonna be the fellows. Yeah, fellows, like feel free to like drop any suggestion, and obviously you cannot ask for this week's assignment.
Yes, I was just gonna say that, not the assignment.
Anything apart from the assignment.
Can you just give a demo where the functions are called automatically?
Example using gelato. I think we are too soon for that. Uh, let's think of something more fundamental. SBT, that sounds fun. Anything else? I think we have only one. All right, everyone is fine with SBT. What's an SBT? Aniket,
What's the
I
SPT?
don't have any
why is he
idea what
in?
it is.
Undo it right now. Yeah, it's a soul bound. By the way, we were good to go with SBTs, right?
Yep, I think sounds good.
Yep, let me just use Remix. I hate Remix. I think all of you will hate it after a year or two, but I think for now it looks good. All right, let me share my screen again. Cool. You guys can see my screen, right?
Yeah, it's visible.
Super. I think I'll need to zoom it if I recall correctly, but I think I have to do it from a different place. Yes, I think it's this one. Yes. Can you guys see it now?
Yeah.
Super. All right. So now when I build the SBT, let's be clear, this is not an ERC 721. This is just a token that is soul bound. Okay. So the reasoning of doing this is literally nothing, but just to kind of see how speed coding Solidity works. I don't really know. But yeah, essentially you have Pragma Solidity, you define the version. I'm using 15 just because I can. Then I have a contract name SBT. Typically your contract name should always match the file name. Some people do it, some people don't do it. I think you should definitely do it. If you don't do it, I don't really have anything to say to you, but I guess it's a good practice. So now let's talk about the properties of an SBT, right? So typically when you talk about a token, it has a few things. It has an owner, it has an URI, it has a token ID, um, and there is also the concept of approvals. I don't really want to tackle approvals at this point of time. So typically what we'll be doing is just a soul-bound token that is once minted cannot be moved from that particular person's wallet, and that kind of shows the URI or whatever you want it to show. So obviously, since we want the URIs, first we need a way to store those URIs. So essentially, we have a mapping, and then we do a UN256 to string. Um, and if we just rename this to token URI, what happens is that the ERC 721 standard requires that every token must have an URI, which technically can be empty. So by making a public token URI function like this, Solidity will create a default function for me called token URI, which when you pass the token ID to, will return the string that we want it to. Now, since we also have the concept of owners, right? So obviously means that we need another mapping similar to event 256 owner, like, and we'll kind of keep it private because it's called owner of. We don't really, actually we can also do this, which is not great, but it kind of does the same thing where this should be address, right? So which means that if you invoke the owner of function with the UN56 will return the address. Now, typically, this will be addressed in a struct, right? Again, it's not a requirement. It can be a struct. I just don't care enough. So we can do it in separate mappings, but this is not a great way to do it. So now we already have token URI, we already have owner of. Let's talk about minting, right? So obviously a function needs to be there that allows you to mint a particular token. And maybe let's say for this particular use case, we want it to be such that it's serial. So we can do something like UN256 private token ID, where we define this as external. So typically anyone can call it and they will mint anything they want really. And so when you call mint, what you ideally want to do is just take owner of set message dot sender equals token ID. And similarly for token URI, you do the same thing. Right. So this will be token ID equals whatever the URI that the user wants to set.
In the mapping, isn't it the other way around? In the owner of?
Yeah, it is token ID, yes. So typically we will not use token ID because it's, as I explained, storage variables are expensive. So you ideally want to call them and store them as less as possible. So typically what you would do is something like event256 current ID equals token ID plus plus. And then you just use this instead. And that is critically, I think, it. I don't know if I'm missing anything. Do you guys think we need more?
Ankit,
Mm-hmm.
as per the C++ paradigm, like current ID won't be taking the updated value of token ID, I guess. You
It's
seem
not the
to
updated
specify.
value, right? It starts with 0. So the first token ID is 0. It's like 0 indexed.
No, like basically we are doing post increment instead of pre increment.
Yes, but the tokens are zero indexed. So there's a zeroth token as well, right? Is there a problem with
Okay,
zeroth
okay. No,
indexing?
no,
What do you think?
anything, anything.
I don't think so. But yeah, like if it compiles, it's good enough to go. That's what I say to everyone. But yeah, I'm just kidding about that. Uh, just to kind of explain about the process of writing contracts as well, right? It is actually fairly wrong. Wrong, I said, but I meant long. But it's also wrong. But essentially, what it means is that typically you would have someone who kind of just envisions a POC from scratch, ends up writing those contracts and the requirements. In the middle, the requirements change like 20 times. And then you kind of end up fixing it each of those 20 times. But ideally, one of the most important components of writing contracts, which I personally didn't agree with until a long time back, was that of unit testing. And the thing is that it is very easy to get contracts wrong. Um, even when it's right in front of your eyes, it is very hard to kind of identify those without writing unit tests and testing for those very cases that you want to protect against. Um, and I say this as someone who has kind of seen some of these hacks go down. And even with unit tests, a lot of them kind of have ingenious either backdoors, I don't want to call them backdoors, or either just plain up negligence that people just
People
don't.
just don't.
You're saying something? Did someone have any questions? I didn't catch that.
I think it was just an echo.
Oh, all right, super. Um, But essentially, what that means is that writing contracts is step one, but testing them is like literally the next step. So it is kind of very important. And then finally, in the life cycle of a contract, it has kind of become so that audits are also like a step. So it means that you would have some time that are kind of occupied for writing, sometimes writing the test for that. And finally, you have like a fixed time period where you're spending like $50,000 to get your code audited by some code audit company, right? Um, and situation is such that the ecosystem is so nascent and that the attack vectors are so new, is that they will still end up getting exploited, simply because we just don't have enough tools for it yet. Because ideally, the situation is such that these are typically things that would be automatically caught by tools, right? And typically, it shouldn't need human intervention. We don't really there should not be a need for a code that we write that needs to be looked over by like 5 humans for 30 days straight to find like the most worst of errors that causes someone to lose like 1 billion in TVL. So that is kind of how writing contracts is. So now I realize that this SVT token is kind of too basic. I feel that I have written. Um, so maybe what we can do is we just maybe introduce a struct. So instead of having like a mapping that looks like this, you would have kind of a struct token which has an address owner and it has an string URI. And then you would kind of only store this particular token. So it can kind of look like this. And in this case, you can kind of do token storage token equals. This is actually like only one way of initializing or like storing in a mapping. There is obviously the other way of storing structs, which looks more concise. But whether it kind of saves gas or wastes gas has to be tested via profiling. So typically, I've seen this save gas, so I have just chosen to use it. But there is like no correct answer, so to say. And typically, Since like there is no transfer, there is nothing. This is a soul-bound token. So typically, an SBT is actually a much simpler thing to implement than a normal ERC-721 because of the nuances around approvals, because of the nuances around transfer from, transfer, and then ERC-721 also introduces this idea of safe transfers, where essentially it has to return the function identifier of safe transfer from um, to receive any particular NFT, which is kind of resolved in SBT because there are no transfers. And yeah, as we can see, that was kind of as simple as what you saw. That is pretty much it, right? We have an SBT, a more fancy one also done. I think that's pretty much it for this part. And the final thing we have is Q&A. So hit me with it.
Okay, I have first question.
Go on.
This is Ashish here. As we see here that you have written one contract, but I feel that, as you rightly pointed out, the main problem lies with the execution of the contract on the chain. So that first, it is very concise. It doesn't take much gas. Secondly, it is secure. So you need to do a lot of testing. So what we have just seen is just writing the contract. I think the major part in the production mode probably is more spent in the testing and the auditing, those kind of stuff. So would we be seeing that as well, the whole life cycle, how you deploy the contract and the security and the audit part of it, as well as optimizing part of it? What are the tools that you use to do that?
That's an interesting question. Whether it will be there is probably a question for the DevFolio folks. But from my perspective, like I can show you how deployment works. It's actually pretty simple. Let me kind of show you that first.
The deployment, I know in the remix you just deploy it.
Yeah, exactly. In the remix, I'll just deploy it. All right. I guess you guys know that much. But what I suggest is instead of doing it in remix, try using Hardhat. Try using Truffle. Actually, Truffle sucks, but maybe you can use Hardhat and you can use Forge, which is pretty good. But typically, it's more nuanced, and it is how it conforms to actual production environments better. So, which is why I recommend trying those more than remix. It is just that it's easy to use, but it's probably not what you'll be using in your real job. And some people actually use it in the real job as well. It is not as bad as I'm making it out to be. But if you have other ways to do it, then why not do it better? Because it kind of you have that entire toolkit that remix won't make it available for you.
Okay, just a quick succeeding question to it. I know that this course is very short, and we probably will not be seeing a whole life cycle. Probably that will take a lot of time. So, can you point to some resource if we are inquisitive to see everything in action, from say writing a contract to deploying the contract and finally getting audit and everything? So, I see a lot of hacks or the cybersecurity issues in these contracts. So, is there a good resource where we can have a look at that and learn ourselves?
So yes, I guess some ways to protect against, like you can kind of learn those things. So there are things called the checks effects interaction pattern. That is, I guess, the most common way of protecting against reentrancy attacks in Solidity, where essentially what it means is that anytime that you make a message call to an untrusted code, it must be a part of interactions. So essentially what happens is typically if a function is calling itself, you can kind of make it do funky things, and you can kind of make that happen as much as possible by providing the gas required for it. So to protect against it, what you do is you have the checks right at the top of transaction execution. So it means that as soon as that check fails, you cannot really execute that again, because that's all you really care against, right? The checks. The checks are the guardrails that prevent these any sort of attacks. So if you are not writing a check for the use case that causes the hack, it is probably the fault of that. And kind of most of these hacks that happen, they are typically because of these reentrancy attacks that someone forgot to catch, or something as basic as like fundamental architectural problems. So, like there are just some things that you shouldn't do, but people still do. Nuances, again, for later. And only a very few percentage of these attacks are like what's called novel attacks or zero-day attacks that we have never seen it before. And those kind of attacks have happened, right? So to kind of give you context as well, we had the DAO hack, which happened on Ethereum, right? After which you had the fork and then you had Ethereum Classic. So people knew of reentrancy attacks before that point of time as well. But the reason it wasn't patched was because the devs of the DAO believed that it wasn't enough of a threat. But that is what it means, right? That if there is an attack vector, it will be attacked. It doesn't matter how small it is or how dumb you think people are. So yeah, so basically, you have to build under the assumption that the blockchain you're working on, Ethereum, Polygon, whatever, it's a dark forest. And at any point of time, you can be attacked. At any point of time, you can be hacked. So you are in a zero trust environment. You have to build accordingly. And obviously that applies to contracts as well.
Thank you, Ankit. I think Aniket, if you can put it into the reading list on Discord, some of the stuff which goes deep into this, I think.
For sure.
Yeah, thank you.
For sure. Yeah, I think Ankit is also there. Ankit, maybe even you can share some links on reading, while I'll also post some of it as well.
Yeah, sure, we'll do that. Like if there are blogs by consensus, there are blogs by I forgot the name exactly. Open Zeppelin, right? So both of those are actually very good starting resources for things like this. If I recall correctly, there is also like a CTF thing by Open Zeppelin that addresses this, which kind of teaches you how to protect against attacks and tries to make you find innovative ways to attack contracts. So you can kind of try that as well.
Hey Ankit, Jayesh here. Could you just explain why proxies are needed in contracts, like to redeploy things? I didn't get the whole the way those proxy contracts access just the code and not the memory.
Right. So you mean storage, right? So essentially, by default, like all code is immutable. So what that means is that once code is deployed at an address, it is never changeable. And that is kind of a built-in assumption with Solidity and with EVM, that once a code is at an address, you cannot change it. You can actually remove it altogether, which is self-destruct. But apart from that, there is really no way to change it. So typically by introducing proxies, what you do is the code that is at a particular address, it basically is coded in such a way that the actual executing code is somewhere else on the chain. So this is what's called a proxy, an implementation of a proxy. So what that means is that, let's say you make a call to a proxy contract, right? And this has the, let's say you have a contract A, and the contract A has a particular function which is just called emit, and it just emits an event. So when you make a call to the proxy contract with that emit function selector, the proxy contract first checks, if it has this function selector. If it doesn't have the function selector, then the proxy function is like, wait, obviously I can't call this function, I don't have it. And this is where the concept of what's called fallback functions come in. And so what the fallback function means is it's basically a special function defined in any contract, which is executed when none of the other functions match the particular function selector. And it just passes that entire data, that transaction call data, to the particular implementation as a delegate call. So now we have the more interesting question. What's a delegate call? You have asked a very meaty question. Good job, Jayesh. So essentially what happens in delegate call is it executes the code of A, so which is the executing the code that is stored at A, while using the storage context of itself. So what that means is that it calls the code for that function selector from contract A. It does those steps, but the state changes are happening in its own context, which is the proxy's context. So which this is the concept that means you're separating the storage from data, where essentially the storage is of the proxy contract itself, but the code is being executed of the implementation contract.
Okay, just another question that suppose we have a proxy factory and it has deployed the implementation first, and then we are deploying a number of proxy contracts. That's the way you do it, right?
It depends. The proxy
Okay.
factories may be a thing, but it depends. Yeah, but go on.
Okay, so does this deployment copy the code, or it just allocates a new memory stack for it?
It
Because
is
this is a
copying
lot
the code.
cheaper, so I'm assuming it doesn't copy the code, but then how does it have the signatures, like function signatures? How does it point to the implementation contract?
Well, it has the code, otherwise it cannot deploy it, right? Okay, think of it this way, right? Let's say you are deploying a contract for the first time. How are you deploying it?
Generally, we have the creation code, and then there's the execution code or implementation code. So the creation code just goes and uh, how do I put it in words?
No,
Okay.
you're right. So essentially what you're talking about is the deploying bytecode. So essentially what is happening is you send the transaction call data and it takes that particular actual bytecode, which is called the code that is deployed at an address, and it puts that onto the blockchain. And typically, the way a proxy contract works, or like, let's not say proxy factory, right? Let's say any contract factory that works is essentially it deploys that particular same code uh, at that particular address. So what it means is that it has the creation code for that contract code in itself. So it's essentially making copies using that creation code.
Okay. So why is this then cheaper?
Why is this cheaper?
Yeah.
It is cheaper in the way that if you were to do this as like just one transaction, you're kind of paying like a base 21K fee, and then you're paying the cost of create two or create or whatever. And then if you were to do it in like a contract call, and if you were to kind of do it in bulk, then you're kind of subsidizing the cost of these initial costs. And that's pretty much it. It's not cheaper in the way that because the OP codes that are invoked are still the same. So for the most fundamental of costs, you can't really save against those. You are just kind of amortizing the costs of doing it over and over. Because if you were to do it separately each time, you'd waste a ton more gas than if you were to do it together.
Okay. Gotcha. Thank you.
Right. I think we are already over time, but no worries at all since Ankit is also on our Discord. So feel free to tag him in the tech discussions channel, or maybe let us know if you want to have a separate channel with technical mentors. We can do that as well. So yeah, thanks a lot, Ankit, for making the time and walking the fellows through smart contract dev, and uh, it's really going to be helpful for them to sort of go with this week's assignment, and also like taking up SBTs as well. Thanks a lot.
Yep, glad to be here. Hope we all had a great time because I did.
Yeah, awesome. Folks, so yeah, I mean, like, I think this was the only session we have like for this week. The rest is totally up to you to finish off your assignments, and also would be a really good time to start ideating on what you want to build. Do communicate it with your primary mentors as well, and also share it with me. And so Srijan, I think we'll be doing an office hour with Srijan from our team tomorrow. So feel free to hop in, and yeah, for sure, Ankit. So yeah, so as I was saying, if you have some ideas ready, feel free to put them down in a Notion or presentation or whatever it is. And I think tomorrow we'll take out some time with Srijan from 8 p.m. to 8:30, in case you want to talk about your idea, have some office hours, and he's the guy you want to talk to about ideas and implementation and stuff. So yeah, I think that's it for today. Any questions, like for me, like for the fellowship or anything? Nope. All good then. I'll be available.
Aniket, I just had
Yeah.
a question.
Yeah.
So, if tomorrow we can have office hours with Srijan, then by what time can we get a confirmation of that, if that's the project we should be building or not?
I like it wouldn't be approved like right away. So like obviously like maybe I'll sort of plan it out key how we can do this in a more formal sense. But obviously any idea should be, it should be there should be a green signal from both mentors as well as us at Devfolio. So I think like tomorrow it would be more. So mostly like tomorrow, it won't be like an initial acceptance, but you can just give him like an idea so that he knows what you're going to build, and maybe he'll give you some more tips or approaches or stuff like that.
And secondly, that our mentors, Raza and Samina, uh, Raza has not, Samina has her
Mhm.
DMs off usually,
All right.
and
So what I'll
Raza,
do, I'll reach out to her with a quick email, and I'll make sure like by tomorrow there is some activity. Venkatesh, I'm assuming like you're under the same cohort.
yes, he
Okay.
is.
Okay. Cool. 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 I'll drop an email to Samina and Raza right away. Great. But feel free to like run it by us as well. I think both of you have sent me your proposals. Srijan and I will also do a quick walkthrough before we get on the office hours. Or we if you want to do it in like separately, like on a one-on-one basis, then I'll figure out something for that as well. Like I'll have a call scheduled with Srijan. All right.
Sounds good.
Awesome. See you folks.
Bye, man. Bye, guys.
Bye.
Bye.